Hello and welcome to the May Recreational Astronomy Night meeting online edition of the RASC Toronto Centre. My name is Paul Markov and I'm coming to you from Markham, Ontario. And aside from introducing the speakers, I also look for presentations for upcoming meetings. If you have a presentation in mind, please get in touch with me. We have openings for the June and later meetings. Our meetings are now held on the first Wednesday of each month. Before we start the presentations, I'd like to thank in advance our technical team comprised of Andrew and Betty Reed, Blake Nancaro, Emma Seabrook, and Ward Legros. Thank you so much for making these online presentations possible for all of us. This evening we have three presentations as usual, and I expect we will be done around 9:30. The speakers for this evening are Andy Beaton. He'll present The Sky This Month, followed by Jenna Hinds. She'll talk to us about the RASC Robotic Telescope project. And then we're going to have Steve Dotson, also known as Stargazer Steve, introducing our next speaker, and that is Alan Ward. And he'll talk to us about optical coatings and oilings for astronomical instruments. And finally, Tom Luton, our president, will close the meeting with the announcements. If you have questions for our speakers, please enter them in the YouTube chat box and Emma will ask the questions on your behalf. And also, if you are attending the meeting for the first time, whether you're a member or not, please introduce yourself, say hello, also through the chat box. I think we're ready to get the meeting started with our first presenter, Andy Beaton, and The Sky This Month.
Am I on? Excellent. Hi, my name is Andy Beaton. I'm speaking to you from my office in the basement at home here in downtown Toronto. And this is my first experience doing the talk out into the void of the internet, and it's kind of spooky. I'm just looking at this blank screen here and not knowing who's out there listening. So I hope we get through this okay. Before I start, I want to say thank you to Dennis Gray. There was a bit of confusion. Dennis did a bunch of preparation for the same talk that I'm doing and very kindly passed over a bunch of notes and useful stuff that I've included into my talk. If you see anything really good, really clever, it's almost certainly Dennis's stuff, so say thank you when you see him. So tonight, we've got the big picture, key dates. We've got the moon, the planets, stuff in the deep sky, double star in deference to Blake, who loves his double stars and has got me hooked on them too. Variable star, and a few highlights of the spaceflight scene in the next few weeks. So starting with the big picture, looking to the west around sunset tonight, assuming that you weren't looking at the same clouds I am when I look out my window here, what we see is our late winter and spring constellations sinking away. Only one planet of real interest right now, and that's Mars. I don't think there's much to see around Mars right now. It's pretty far away and getting pretty close to the sun. When we get closer to the next meeting, which I believe is June 2nd, and look at the morning sky, there we see some action. We can see the moon will be up, but we've got a whole parade of planets, starting with Pluto. I'm giving it planet status for this anyway. Saturn, Jupiter, and Neptune. Uranus comes up a little bit later, but it won't really be visible. At the same time, we're going to have all our big summer constellations, and by dawn in June, we'll even be starting to see the fall constellations. The nights are getting longer. This is we're the people who are most upset about this. We're getting less and less observing time as we get closer to the summer solstice. Tonight, astronomical twilight ends at 10 after 10. That's local daylight time, and starts again at 3:45 in the morning. So you've got 5.5 hours of proper observing time. By the time we get to June, then we're looking at well past 11 before it gets reasonably dark, and almost 3 o'clock when it starts lightening up again. So if you've got your deep sky photography projects lined up, you're going to have to spread them out over a few nights. So important dates. The new moon is on May 11th. That's the big one. Moon is at apogee on May 11th and perigee on May 26th. Apogee is close. No, perigee is close. Apogee is far. If you have a camera on your telescope, it's probably worth taking pictures of the moon at these two dates and comparing the angular size of them. It's interesting to see how the moon grows and shrinks as it approaches and disappears. Full moon is on May 26th, and it is a supermoon, and it's more than a supermoon. It's a total super dragon blood moon lunar eclipse. It's the whole ball of wax all at once. I don't really love these supermarket tabloid descriptors of lunar activity, but I can assure you that people who are not deeply into astronomy pick them up, and they're going to ask you about them. So I'd like to, at least be aware that these things are happening. We have the Eta Aquarid meteor shower, and it peaks tonight, tomorrow morning. So if you are under clear skies, then I would advise you to go out and have a look. It's not quite a Perseid quality shower, but it's a good one. There's going to be a few dozen per hour, so get out if you can. And on May 12th, if you're in New Zealand, you'll get to see Venus occulted by the moon. Normally, I wouldn't bother telling people this, but because nobody in Toronto is going to see it, but since we're out on the internet, I have no idea who's going to be listening to the conversation over the next month. So, maybe someone from New Zealand is going to pick that up and see the occultation, and my effort will not be in vain. So we've got the moon coming up. First quarter on the 19th, full moon on the 26th, last quarter on June 2nd, the day of the next meeting, and May 11th is our new moon. Now, for people who are keen on trying to find the lunar X, that's a feature of the moon where you get light coming from a certain angle, lighting up the rims of two craters. It makes it look like an X. You can Google it at your leisure and see exactly what it's supposed to look like. But May 18th, starting around 7:41 Eastern Daylight Time, I've done this Toronto time. If you're looking from another time zone, you can probably do the conversion yourself. But that's when that is. May 26th is our total lunar eclipse. Best viewed from the South Pacific. If you're watching from Toronto, it'll be setting around 5:30 in the morning, depending on your horizon. If you're in Toronto, you probably won't even have a horizon. The moon will barely be entering the umbra at that point. And as I mentioned before, people are going to be hyping up the supermoon. A supermoon and a total eclipse together, that's got to be good for attention from people who really don't know anything about astronomy. And if your relatives are like mine, you're going to get all kinds of requests for information. What's a supermoon? What's a blood moon? And this is your chance to spread some science around, spread some useful information, tell them how things work, tell them that the Earth isn't flat, and that's why the shadow of the moon is round. Full details are on timeanddate.com, and I believe they'll be live streaming the eclipse as well. And I imagine as we get closer to that date, more websites will crop up with a live stream as well. So we get our usual planets. Mercury will be slowly appearing in the evening over the next month, and then it'll pop up as high as it goes, then pop back down and fade as we get closer to June. Venus is slowly rising in the evening sky, and the longer it goes, the brighter it's going to get, the more obvious it's going to get. By summer, it's going to be insanely bright, and no one will be able to miss it. But yeah, it might be an interesting project to see how early in the cycle you can see it. Mars is disappearing into the evening twilight. It's tiny. It's low to the horizon. It's going to be washed out by twilight. I'm not sure I would even bother looking for it at this point. I mean, interesting to see it, but you're not going to see anything like ice caps or rovers or anything fun. The big planets, Saturn and Jupiter, they will be rising in the morning sky. Saturn first and Jupiter after. They're both at pretty low declinations down in the Sagittarius area, or the one beyond it, Capricorn. They'll be at low declinations, so you're not going to be able to see an awful lot of good visual detail, but you're definitely going to see moons and rings and all the stuff that that people like to see when they look at Jupiter and Saturn in the telescope. Now, this is something that I got from Dennis, and I'm grateful to him. Mutual occultations. It turns out that the Earth is crossing the orbital plane of Jupiter's satellites between March and November. Happens every 6 years. And what's going to happen is we're going to get events where the moons of Jupiter are eclipsing each other. And I've got to admit, I've been looking at Jupiter for years, and I've never seen one of these, so it's a thing to watch for. There's a website here. I believe the talk is going to be posted online at some point, so you can scoop it up at your leisure. Otherwise, I'll get it posted somewhere on one of the RASC websites. But it has a list of the events. The ones that are worth watching for this month, May 11th, Europa is eclipsing Ganymede. May 20th, Io is eclipsing Europa. And May 25th, Io is eclipsing Europa again. Yeah, this is a cool thing. I've never seen anything like this before, so I'm going to have to watch for it. Clear skies permitting. Uranus and Neptune. Uranus is too close to the sun this month. We're not going to see it. Neptune, if you're up early in the morning before late May, early June, then you should be able to see it. With a reasonable sized telescope, you should be able to see not only Neptune, but its largest moon, Triton. It's a bit of a challenge. It's a 14th magnitude or so, but I'm pretty sure many of the people watching here have a telescope powerful enough to look for something like that. On the whole, not a great time for the ice giants. They're fairly low to the horizon, even at their best. But yeah, they're there, and if you're in the mood to look for giant planets, there you go. Pluto and Ceres. We can quibble about whether they're planets or not. I don't think they are, but I'll call them planets for the presentation. Pluto's in Sagittarius and is finally getting away from the Milky Way, so it should be findable. It's about 14th magnitude right now. 10-inch or larger scope ought to be able to find it. The best way, as always, is to take a picture and then take a picture a few days later and look for it moving, because even if it is visually findable, it's going to be tricky to see with to distinguish it from the background stars. Ceres this month, too close to the sun to observe, so I think we're going to have to give that one a miss. So I like to throw in a bit of deep sky stuff all the time. M51 with the Whirlpool Galaxy is the one I thought of this time. And there it is. Everyone's seen the picture of it before. It's an excellent target for this time of year because it is so bright. It's a face-on spiral galaxy. If you can get out of the city under good skies, you can see spiral structure with an 8-inch or larger scope. 6-inch, you can see the spiral arms, but it's kind of hard to figure out, what they are or how they're connected. Just about any telescope would also pick up the companion galaxy. So you're seeing two interacting galaxies at once, which is always a fun one for the bucket list. And our picture. Now, if you're a more experienced observer and you've seen M51, you finished your Messier list, there's still stuff to look for. Looking for the bridge of matter connecting the two. It is visible to invisible light, needs a large telescope and a good dark sky, but it can be done. Looking for the H2 regions in the galactic disk. That's all these red splotches all over the place. It can be done with a large telescope. If I were to try it, I would try it with a filter and a camera and try and get a picture of them. It's a challenging thing with the human eye, but because they're that beautiful hydrogen red, it's easy to filter out. In fact, if you have a filter, you can probably do it in the city as well, because there's not a lot of hydrogen emitters in downtown Toronto. M51 is also the source of a lot of way more supernovas than we would expect. We've had them in 1997, 2005, and 2011. I don't know whether it's just a weird coincidence or whether there's something about this galaxy and its interactions that make it a supernova hotspot, but it's probably a good place to try visual supernova hunting. It's a thing that can still be done. Some people are still doing it. And it's close enough that a supernova should be visible to a modest 8 to 10-inch sized telescope. So we have comets and meteors. The Eta Aquarids peaking tonight, but continuing on until May 28th. Obviously, we're not going to be the peak number of meteors, but we should still be able to see some. Smaller meteor showers or meteor dribbles, the Eta Lyrids, the Tau Herculids, and the daytime Arietids throughout the month. I wouldn't go out to look for them, but if you are out and you see a meteor, you can see if it traces back to one of these vectors and try and figure out if it's a part of a known shower or just a sporadic meteor. The daytime Arietids, that might be a tricky one because obviously it's daytime, but if you're interested in the project of setting up a radio receiver, tuning it to dead air, and if a meteor comes over, the ionization will reflect a radio station from well out of your normal range. You'll get a sudden burst of voice or music. That's a project worth doing, and it's especially good in that it can be done in daylight. It can be done in rain. You can do it any time that you can't do regular astronomy. So we got some comets. C2020 R4 Atlas is the big one right now. 9th magnitude in Corona Borealis. And Dennis was kind enough to cook up this little map for me. It's not too far away from M51 now that I think about it. Just south of Canes Venatici. But it's moving fairly quickly and it's fairly bright, so it's going to be the comet to see. I would say it's a good time to either track it down by the internet or any astronomy software, because it's going to be in a different place every night, and I don't think I can really show you how it's going to be whenever it turns out to be clear where you are. We've got 10P Temple 2 in Pisces, C2020 T2 Palomar in Canes Venatici, and C2019 L3 Atlas and Perseus, all of them brighter than 12th magnitude, which makes them visible to a reasonable telescope, skies permitting. There's a map again. So I've picked a pretty bright and obvious double star this time. Blake likes to go for the obscure ones, but I'm hitting for the people who have not got a lot of observing experience here. Also known as Cor Caroli in Canis Veritisi. The Observer's Handbook gives it 3 exclamation marks for its amazing beauty, and it really does look great when you see it in telescope. One is definitely blue, one is a good deal whitish. They call it green, but it always looks white to me. People who have talked to me about astronomy before know that variable stars are my own particular obsession. And one of the reasons I did pick Alpha Canis Venitasi is that it is slightly variable. It's an interesting one in that it suffers from many giant sunspots from strong magnetic fields, which leads it to vary in brightness about 1/10 of a magnitude every 5 days or so. It's a tough one to measure with the naked eye, but if you've got a photometer on your telescope, you could probably go out and measure it. And if you don't want to go out and measure it, you can just go out and enjoy a staggeringly beautiful double star. So since I've told you about a variable star under the guise of double stars, I've gone for not a variable star under the variable star heading. What I've picked this time is 3C273, a quasar in Virgo, a galaxy undergoing an explosive event at its core, and it's been going on for a long time. It's about 2.4 billion light years away, and it is the farthest thing I have ever seen with my eyeball. It's about 12.5 magnitude. It's got a 6-inch or larger telescope and dark skies. You should be able to see it, and it looks very much like a star. It is powered by tons of material spiraling around the supermassive black hole at its center. And as it as material spirals in, it blasts off tons of radiation, which is what we're seeing in the form of light, and massive jets blasting off into space as well, which I don't think any of us could see, but it can be done with a large telescope and a long period camera. Now, the cool thing about it is because it's a black hole, it's a very compact object, it can change its characteristics very fast, which makes it suitable for amateur observation. A lot of variable star observing has been made slightly obsolete by all-sky camera surveys. You know, they'll take a picture tonight and they'll take a picture next week. And your long-term variable stars will be carefully measured automatically. But when you're looking at a quasar, it will change very rapidly, over the course of hours, much faster than the sky surveys can keep up with. So it's actually a really good target for us amateur data collectors. As usual, aavso.org is the place to go for finder charts and more information on how to observe. I strongly suggest everybody give observing variable stars a try, because it's fun to be able to contribute actual data to science. So coming up in spaceflight highlights, I mean, the big one has got to be Perseverance and Ingenuity on Mars. I think everybody is looking forward to seeing helicopters flying around Mars, taking amazing shots and views that we have never imagined until now. India and China are both launching space missions over the next few weeks. The exact date was still to be determined when I put this together. Tianwen-1 is projected to land on Mars sometime within the next month. That will be worth watching for. I don't think we'll get quite the same coverage as we did when Perseverance was on its way down, but we've got to watch for it anyway. ISS passes late at night, early in the morning, just about every night until the next meeting. Dennis has picked out a particular favorite, May 24th at 1:40 a.m. The ISS is potentially going to pass between us and the moon if you're viewing from the Mississauga area and the orbit hasn't been altered. I haven't seen a lunar transit myself, but I have seen pictures that people have taken with the space station silhouetted against the moon, and it's pretty spectacular. And heavensabove.com is your best place to go for up-to-date information on when and where the ISS and other space missions are likely to be. And once again, what if it's cloudy, which it very often is. I will suggest visiting zooniverse.org, where they have a heap of citizen science projects, which mostly involve taking data that's been collected by telescopes and observatories throughout the past few years and putting human eyes on it. Turns out that humans are much better than machines at picking out the anomalies that these scientists are interested in. So we have a dark energy explorer examining distant galaxies, looking for evidence of dark energy and expanding universe. Disk Detective is searching for planetary disks or protoplanetary disks around other stars. Bursts from Space is working on looking for matches between radio bursts and visual objects. And Radio Galaxy Zoo is a project where they're getting people like us to classify galaxies by their radio signatures. All stuff that anybody with an interest in science can get involved in. You just click on the link and everything gets spoon-fed to you. So it's a good way to get involved. And that is what I have for this month. Thanks for your time, and I hope we all have some clear skies.
Andy, thank you very much for your presentation. Great content, great delivery. We're going to have you back.
All right.
So
now that I know my computer works, I can do it.
I'll be in touch. So let's go to the internet. Let's see if there are any questions for Andy.
We do. We have one question coming in from Blake. How do you measure variable stars, and do you use a photometer?
There are a couple of ways to measure variable stars. You can use a photometer and carefully measure the amount of light you're getting, but the way I do it is through visual means. I've downloaded charts from the AAVSO, and it has the star that I'm interested in and neighboring stars of known brightness. So I will take a look at my target star, compare it to the this 11th magnitude star over here, this 12th magnitude star over here. It's about 3/4 of the way between the two towards the dim end. So I'd say it's probably about 11.7. And as it turns out, human eyes are remarkably adept at that kind of interpolation. They, 1/10 of a magnitude estimates are commonplace. Some people can even do better.
Thanks. Which scopes do you use for the variable stars?
What I use is an 8-inch Schmidt-Cassegrain right behind me here. I use that, and the widest eyepiece I have, it's a 30mm Plössl to get the widest possible field of view. If I'm looking for something down near the limits of the telescope's ability to grasp, then I'll use a higher magnification eyepiece and get a closer look. As it turns out, the dimmer the star, the more variable stars in the same range are going to be available for comparison.
Bruce wants to know what's in the stars for the Leafs.
Having following the Leafs since 1967, I predict an outstanding playoffs until they choke in the semifinals. That's the Toronto way.
That's all the questions. Thank you.
Okay, thank you.
I'll just throw in a comment in regards how to measure variable stars. Some time ago, Dennis Gray delivered a presentation to us about using a DSLR camera for measuring variable stars. There's some freeware applications out there that can be coupled with a camera, digital camera, and they can output the magnitude of the star. So that's something to you can search on the internet for if you have a DSLR already. And of course, CCD cameras as well can be used. All right, so thanks again, Andy. Let's move on to our next speaker, and that's Jenna Hinds, and she'll talk to us about the RASC Robotic Telescope project.
Thank you so much, Paul. I'm Jenna. I'm the Outreach Coordinator and the Robotic Telescope Project Lead at RASC National. I am coming to you from the same room I've been in for months in Toronto, and I'm going to talk to you a little bit about the Robotic Telescope Project. It's a fairly large project, so I'm going to focus on a couple smaller areas of it, but I'm also going to tell you about how you can get involved at the end as well. So the Robotic Telescope Project started in 2018, I believe, a little while ago, and before I was hired on at the RASC. I took it over in 2019, and the goal of the project is to provide a research grade scope for people to use in the RASC to keep themselves from going bonkers in the winter. So we really wish we'd gotten it up and running before 2020's winter. Unfortunately, we've hit some delays, but we're getting really close to getting it up and going, and there are still ways that you can participate. This is the scope for those of you who care about gear. All of the details are on the left for what the hardware is. There's also, so you can see in this picture, this is the scope here. It's actually in moonlight at this point, and that's a DSLR camera strapped to the back of it with all of the imaging stuff back here. The scope is fully remote and robotic. It operates out of California in the Sierra Nevadas for the clearer skies and all of that. We did run into a bit of a hiccup with the fires last year, but that's all been sorted out, and now we're back to some excellent imaging. You can also see the scope online if you're interested. I believe the link will go out in the YouTube chat to sierraremote.com. This is our telescope here on the right-hand side. This is on the one of the building view pages that you can take a look at. At night, occasionally you can see it moving around, which is kind of fun to watch. If my screen sharing's all good on this, I'm going to just quickly jump over to the website, which is here. This is Sierra Remote, their telemetry view, and this is where we can get details on what the weather's doing, what the seeing's like, whether or not it's getting humid, and at night, of course, it's not night in California, it's not even night in Toronto yet. We can see what the sky looks like as well. Our scope is in Building 9, which is this one here. And if you want to see our scope in particular, you can go to Buildings 1 to 9. I believe it's the 5th one down. There it is. All right, back to the slides. So the scope has a CCD camera attached to it, and then they have the DSLR on the back. So if you're looking at the views of the two, these are the two views. You get the DSLR view here, and it has a 200mm fixed lens. So it's a nice wider field of view compared to the CCD, but relatively tight in for everything else. And then that's the little CCD chip there. If we were to take a picture of this, this is what the DSLR would come back with, and this is what the CCD would come back with. So when the scope was purchased, and sort of the long-term goals of the project are to make astrophotography and science more accessible for people. This is obviously a very expensive rig, and not everyone, most people can't afford or have no interest in running a rig like this, but they do want the pretty pictures out of it. So that's part of the goal, is to provide the data to folks who are interested in getting into astrophotography, but at a price point that is more accessible to people. This is from I believe, we took these photos. And this is actually available if you want to practice. We did run some astrophotography processing contests with Sky News in late 2020, so August, September, and October. And we have sets of data that you can practice with that are available to the public if you'd like to give it a try. It does come in at least 2 of the contests come in 3 packages, which was set up by one of our members on the team, which was really, really great. Completely raw, unprocessed data with the calibration files there as well, so that you can calibrate it all yourself. You do control every step from start to finish. Then there's another set of data that is calibrated but not stacked. And then there are master frames for each of the filters. So it depends on your experience level. I am not an astrophotographer, so I go with the stacked for me by other team members option. I'm getting there, but I'm not confident in my skills yet. And I believe that's what Jeff Dutton did. So you can still get some really beautiful pictures out of it, even though someone else is doing it for you in some ways. And Jeff has been fantastic to watch. I don't think he's in the audience tonight, but he's been fantastic to watch because he's bought access to the rest of our data and has been working super hard through it to improve his skills. And he's been sending all these photos in to show how his skills have improved over time. It's really cool to see that growth. There's some more astrophotography photos in case you're interested. These are a couple of my favorites, which is why I included them. There's a sample of the DSLR on the back of the scope as well. And then I wanted to show you one of the cool projects that we worked on last year. This was leading up to the Jupiter and Saturn conjunction that happened on December 21st, 2020. And the reason, so we have those 2 cameras. The CCD chip is not really set up to take planetary photos. The photos just don't turn out that well. It's set up for deep sky photography. Technically, you can take photos of the planets, and we did, but they're just not very good. So we came up with a different project, which was to image Jupiter and Saturn with the same framing over a couple of weeks to watch them catch up to each other. And that's what, hopefully this will load enough. That's what this shows you. We did have clouds on a few nights, and the tricky part too was that they were very close to the horizon, which meant that you can see in a couple of these, the roof was in the shot. The roof of the observatory is in the bottom corner. We do have some more photos. We got about another week of photos after that. I just haven't ended up collaborating them all yet and putting them all together. It was really fun because it involved working across teams, and it involved a lot of people learning new skills. So it was a good time. It was also really fun to show things like, if you look up really close, you can see the movement of Jupiter's moons and Saturn's moons as well. Saturn's one moon, the one moon that's bright enough to see, which is Titan. So it was a pretty cool demonstration, super fun, and a neat way to look at the conjunction for sure. Okay, so that's all sort of a background of what the scope can do. And then there's a couple, here's the biggest thing that we have been doing with it so far, which is working in classrooms. We started this project which pretty much when I took over as lead in about September 2019. And we ran a test sort of like pilot year on this project where we got students looking at exoplanet data and collecting their own exoplanet data with the scope. So the structure now of the program, and then we have made small improvements, but it stayed more or less the same. The students learn about exoplanets and how to detect them. They choose their own exoplanet to image. We help them, of course, with every step of the process. In this case, we give them all the specs on our scope and what it can see and where it is, all that sort of stuff, and tell them to search a database and show them how to search a database to find exoplanets that would be good candidates. They join us for a virtual field trip, which is great because this was all developed before we were virtual. So this ended up being a really nice transition into the virtual world, where we jump on the telescope from here, from our computers, because it's all remote, and show them what's involved in taking data. So that's programming the run, starting up the scope, cooling down the chip, all that sort of stuff. They also have the option to learn how to process that data, so like calibrate it and fix meridian flips and all that sort of stuff. There's a more intense version where they can do that. And then finally, they can produce a transit graph of the selected exoplanet. Quick overview for anybody who does not know what we're actually looking for. You're looking at a single star and waiting for a planet to pass in front of it. Obviously, you can't image that with scopes from Earth terribly well, from space a little bit easier. but still very difficult. So what we're looking for is, let me just grab my phone. What we're looking for is brightness of the star dimming a little bit as the planet goes in front of it, and then brightening again once it leaves. So that's what we're looking for in the scope. And the reason behind all this stems from my own personal issues in high school, pretty much. I found in high school that I did not really get the scientific process in science class, and it was always about learning what we already knew. And it is that way until pretty much the 4th year of undergrad, right? You're just learning what other people have already figured out. Even in labs where you're doing doing titrating stuff or trying to pull DNA out of bananas, it's been done before. Every student before you has done it. Last year students did it, year before students did it. If you're not getting the right answer, the problem is with you. It's not with the data. So that's not realistic. That's not what science is like. And so I wanted to give students in high school an idea of what science is actually like in terms of discovering something new for the first time. This is it's not obviously not fully discovering something new because we're getting our hypotheses from a database where there are calculations about what we expect, but they get to be there and watch the photos getting taken as the event is happening. No one else, at least in their world, is getting this data. We're not giving this data to anybody else but this group of students. They can't Google what to compare it to. That's the key for me, because it's so easy to Google what was I supposed to get out of this experiment, and they can't Google that. So that's the reasoning behind why I started the project in the first place. Luckily, it has been successful in that capacity. It's also exposing students to university level astronomy for the first time, especially and just to be clear, I don't know if I mentioned this is targeted to high school students. So grade 9 to 12 sort of range, depending on how ambitious they are. So it's exposing them to that university level astronomy, which I think is really important in high school as well, because what if you don't like it? What if you get into astronomy, you get through a 4-year degree, turns out you hate it? Or what if you think you won't like it, and then you see it set up in this way, and then suddenly you do. Astronomy is often not quite communicated as what it is in the academic world. Like if what we do in terms of going out and looking at space through a telescope, most academic astronomers don't ever need to do that. So that's what we're kind of showing them by taking them through this program. The program's also been a great addition to some resumes. Of the test group that ran it in 2019, 8 students did the program, 4 got internships at different research facilities. So, and I think all got accepted to their astronomy programs. So it's shown this really nice trend of getting students to where they want to be. And then the final reason for doing it is to help teachers who don't understand astronomy. The whole program comes with PowerPoints and training guides and lesson plans and labs, and everything's all written up so that the teacher who may not know much about astronomy can jump right in and deliver the entire program and learn themselves that maybe astronomy is not so terrifying to teach. You can find out more and apply if you want to at eduscope.rasc.ca. That's not that site. That's not that site. It's this one. It has all the resources for teachers available once you apply. It's got forums for students to talk to each other. Students can post stories about finding objects. And then eventually we can have those stories possibly published in other RASC publications like Sky News and the Journal, depending on how things go. That happened last year. This was a post by that test, or an article by that test group at John Abbott College. So there's 2 different programs that you can do. We have an advanced program and a basic program. We started off with just one, and then we realized that was like completely unfeasible for teachers in classrooms. The program very much, it took a lot of time. It took time outside class. It was quite heavy in terms of workload, and it required that the students were pretty motivated. So that program is now the advanced program, and it's aimed mostly at clubs, individual students who are maybe doing science projects or science fair projects or end of term projects, extended essays in the IB program, that sort of student driven question. It's a little bit more in depth where they get their own target and they choose it themselves and they have the data just for them, and they can watch their own data being taken, which is kind of cool. And it does provide that opportunity to publish as well. And then the basic program is a little bit more dialed back, a little bit more relaxed. The data is already processed, already packaged up and ready to be analyzed by students. There are choices in which kind of data they use if they want a bit more challenge. We have a couple data sets where there were clouds, or the exoplanet went too low in the sky and it hit the roof of the observatory. So sets that are a little bit more challenging, and then we have sets that are like perfectly fine, guaranteed to have transit in them. But the students still have to do the analysis themselves. And they can still join for their virtual field trip, but they don't get to see their own data getting taken. They only get to see the advanced classes data getting taken. The main difference is that in the advanced program, it's student driven. So the student is the one who's often coming to us and saying, we want to do this project, or I want to do this project, whereas classrooms are more teacher driven. So the teacher is coming to us and saying, I love astronomy, or I really want my kids to get more of an experience. How can we fit this in? There's an example of a plot for HAT P16b. This is essentially what you're looking for is the brightness of the star, the planet dipping in front of the star, the brightness dipping as the planet moves in front of the star, and the star brightening afterwards as well. And there's all the check stars to compare it to. So far, it's been a really great success, and it's been really fun to run. I'm running it with a colleague of mine as well, and we've ended up staying up until like 1 in the morning with classes of students and their teachers, all who are just absolutely fascinated by it and want to like check things out and try taking extra photos and all that sort of stuff. So it's been a great success. It's been really fun. Last week we had a high school club of 11 students and 1 teacher. And it was so exciting to see because it was all women and non-binary folk in the club, which I've never given a presentation like that, I don't think, ever before in my life. So it was really, really, really great to have that experience. Okay, that's all well and good. If you're a teacher or a student, you don't get to do that. So how can you participate if you're not either of those things? We do have a couple different options. Some of them are at different stages of rolling out. So we have our first one is a data user, which is just purchasing access to the data that we've collected over the past year. It's sold on a yearly basis. 2019 and 2020 is lumped together because it took us so long to get this project going that we felt bad. So you can get 2 years access for the price of 1. And the $50 price tag is for students. So students are half off for everything in the program. As we get our new database system up and running as well, we will also have discussion forums just for data users who can talk to each other about how they process the images, and ask for tips and tricks and that sort of stuff. Then we have team users, which is more of an experience, which sounds really annoying when I say that out loud, but it is. It's meant to provide people who join the team with more of an experience when it comes to choosing targets and processing the images, what's involved in acquiring the images, learning how to use the software. We expect this to be popular among people who are interested in setting up their own remote observatories. For me, when I was learning all this stuff, that was the most fun part, was figuring this stuff all out. So it's meant to provide that educational experience and support and training when it comes to this kind of software. You also get first dibs on the photos, which is kind of nice. We considered using software, for those of you, I'm sure many of you are very experienced who are watching, so would know this, but it's called ACP. It's software that you basically put on your computers and it does everything for you. We considered using that, which would certainly make things more efficient. We wouldn't be staying up until 12 in the morning to turn the scope on, but it takes away the learning experience and it makes it I don't want to say it makes it too easy, but it's just not as fun. Like, it's so much more fun to hit the button and take the photo yourself. And that's the experience we want to provide for the people using the teams and the students themselves as well. I accidentally once said that in front of the developer of ACP. That was a fun night. It is. I like the software in general, but just doesn't suit our specific needs in this case. Timeline-wise, the data is available now. A lot of this is dependent on us having a forum system to talk to each other. We don't have a forum system, or we didn't have a proper forum system until like Monday. So we're rolling that in, that's this database thing I'm mentioning. That's coming into place right now. So by July, we should have some forums up and running for participating on the photo team. So the photo team will be available soon. They've been working really hard to set standards for the images and making sure that everything's consistent, and there's a process in place to make sure that the flow works well before we open the team up to new people. And then in the future, there's a possibility we do have a science team in place right now who's sort of developing a baseline of science material, but the future of the science team is a bit uncertain. Long term, we expect to be working with, we expect to find funding through grants to help us bring in grad students who can run projects on the scope, and we can offer volunteer citizen scientists who would like to help. We're going to be running some programs about how to detect exoplanets, which is obviously, or it may not be exactly what the students would be working on, but it's a start into that sort of scientific processing world. We'll be offering training programs on that in the summer. We're also working with Sky News to make this accessible. I believe Alendria is watching right now. Alendria is the editor-in-chief of Sky News. We're working with them to make data available just to the Sky News audience. I believe as RASC members, you are all technically in the Sky News audience, so that counts. And I believe Sky News subscribers who are not RASC members will also have access to the data. And the plan is to do something similar to the photo contests we were running. And Sky News will cover much of the costs required for that. There may be a pay by the hour option eventually where anyone who's a RASC member can jump in and just buy time on the scope. At the moment, we don't have the staffing to make that a reasonable possibility without me pulling out all of my hair. So we'll get there. Sky News is kind of bridging that gap while we find a strategy that will work better. And that wraps up the everything. I believe in the YouTube chat, there should be links going out if you'd like to purchase the data. It's available for purchase if you would like, and we'll get you hooked up. It's all in a Google Drive, and you can download it from there. Again, that data is also packaged in such a way that there's an option for calibrated images. And that's it for me.
Great, thank you so much, Jenna. I didn't know most of this. Fabulous to know that so much is available to students and teachers and members alike. So I'm glad that you agreed to present to us. And perhaps in the future you can come back and give us an update once things develop.
Hopefully you'll have some you'll have some members who are interested in participating on the photo team who may be able to update you as well.
True, very good. Let's go to Emma with questions.
Okay, first question is, what is the resolution of the rig with the CCD at prime focus? Okay,
so I am not an astrophotographer, if I have not made that clear. It's a 4K by 4K chip. So that is, in theory, that's all as far as like what it can resolve. That's what I know about the size of the chip. I don't know how to figure out what the resolution would be at prime focus, I'm afraid. I am the lead of the project. I delegate a lot of the knowledge having to other people.
Okay. The AAVSO collects exotransit data as well as variable star data. Would your students be comfortable submitting their data for real research?
Yeah, I think a lot of them would love that. If I don't have too many connections at the AAVSO, I think I know one person. So if someone can connect me with them, email is there, and in a way that would be useful, I think the students would be absolutely thrilled to have their work be properly used for science.
Great. Are they publishing their results, and if so, where?
So this is dependent on the students. It's an extension of the project. If they want to, they have the opportunity to submit articles to Sky News and the journal. There isn't necessarily a guarantee that they will be published, but they can submit them and for consideration. The sort of lens we're putting on it as someone who is not an astronomer and who is instead a science communicator is if they would like to write less technical pieces, so talking more about their experience or this, story behind how they got into this or why they're interested in space or whatever, that's more of a Sky News piece. And then if they're just writing about the science of it, if it's like an extension of their lab report, then that's more of the journal audience.
Do their peer-reviewed published reports get to NASA or other relevant organizations?
Sorry, could you repeat the first part of that question?
Do their peer-reviewed published reports get to NASA or other relevant organizations?
We haven't had any of the students take us up on writing a scientific report yet. So the ones that have participated have written less scientific stuff, more casual reader stuff. And so in theory, that would be really cool. Again, I don't actually know where we would send them to for that. So if someone knows where we're supposed to send things like that, that would be great. Otherwise, I'm not sure how to make that connection. So please do pass that knowledge along to me.
Is there an age limit for the programs?
No, technically not. You do have to apply. When it comes to the basic program, that's been pitched more towards grade 11, grade 12, Earth and space sciences, math, physics, and if there's an astronomy component, in some provinces there is, in some provinces there isn't, those kinds of classes. The individual program, it really depends on how ambitious the student is. So right now we're working with a club that is mostly grade 9 to 10 students. We've also worked with one university class, college class, and we've also worked with CEGEP students. So it depends on who's interested and how ambitious they are. Generally speaking, in my own personal sort of like sorting through people, I usually, or if I'm telling a teacher, I usually say about 8th grade up. Kids are really smart. So I don't want to stop them from if they're going to participate at a younger age. I just want them to know that what they're getting into, if that makes sense. So if we were to have a student who wanted to do a science fair project, for example, and they were in the 6th grade, I wouldn't say no. I just make sure that they have the right support in place to help them through it. So no age limit.
Thanks. How far in advance does someone have to book use of the robotic scope?
We haven't got this particularly nailed down because we are still in our first year of having this website in place and having an application process and all that. Before we were just doing it sort of based on word of mouth. So there are cases where, like, if you wanted to apply now for over the summer, we could do that. If you wanted to apply now for maybe even June, we could do that. It depends on how many other people have applied. We will eventually put a deadline in place for the advanced program because there are limited nights. We only use the scope once a week. And so we only have one night per week to run data collection nights, and we have issues with weather sometimes. And so we usually save 2 nights for an individual class. And for that reason, once it's booked up for the season. Excuse me. So there's a little bit of wiggle room there. If you're doing the basic program, you can do it literally anytime. You can just log right on and download the data, no problem.
Okay. Is the equipment owned by the RASC or leased from the facility?
It's owned by us. It was purchased in 2018, I think. Some of it was donated. A lot of it was donated. I believe a couple of our computers, I think maybe both of our computers were donated, as was the camera, the CCD, I believe, and the DSLR. So we've gotten a lot of donations, but yeah, it's ours, and we rent from this facility.
Perfect, thanks. That was the last question.
Yay, excellent, good stuff. And I know this comes up a lot with the scope, because there's been a lot of discussion over the years about the origins of the project and whatnot. The scope is entirely supported financially by user fees. Usually that's grants, but for the most part it's, and for a while actually now it's been large donations from the people who are on the founding teams. And then we will, as we move into the new system, it will be user fees as well.
Thank you.
Thanks for having me, everybody. This was fun.
Great. Thanks again, Jenna. Fabulous presentation. Let's move on to our next speaker, who will be introduced by Steve Dotson, also known as a Stargazer Steve. Our next speaker is Alan Ward. He'll talk to us about optical coatings and oilings for astronomical instruments. So go ahead, Steve.
Oh, okay. So it works better with sound. Okay, how are we doing? I'm speaking from Alan Ward's vacuum coating room in his backyard shop in Sudbury, Ontario. And I have known and worked with Alan ever since he started his prolific telescope making career about 40 years ago. Several years before that, as a teen, he had become fascinated with the possibility of making your own telescope when he read an article about it in the Popular Science Encyclopedia. But one sentence that you can see in the yellow stopped him cold. You have to send your work away for the shiny aluminum coating. Fortunately, that dream of telescopes came back into focus when he met Sudbury's telescope pioneer, Ken Odaisky. Ken had made a gaggle of scopes, many with mirrors he had silvered himself. With Ken's example, Alan quickly gained experience and became a telescope mentor to many at Science North. Of course, Alan soon realized you could skip the send away part of the mirror making by making a lens instead. So Alan's next telescope was a refractor. Now he makes world-class apochromatic refractors that have won many prizes at the world-famous Stellafane convention. But Alan was far from done with mirrors. The next bold step was to renovate several mirror coating plants and become an expert in their use. And some of you may have seen Alan at Starfest in 2003 when he successfully illuminized a telescope mirror in the field with his portable coating plant. More recently, he transported that equipment 1,000 kilometers to Stellafane in Vermont to provide the first ever illuminizing service there, coating 15 mirrors as a convention volunteer. Some of the people will recognize the man on the right is Al Nagler of Eyepiece fame. Few people know the theory and practice of what goes into and on astronomical optics like Alan. So I'll turn it over to him now.
Well, thank you very much for that, Steve. And I can't believe that 40 years has already gone by. And wow. And another thing too, this year actually marks at this meeting, this marks my 25th anniversary for actually giving this talk. So I started giving these talks on coatings back, my first one was done at the University Star Party in 1996. So we're running short on time. So I'm going to go through this pretty quickly. And I'm sure you're all going to find this topic quite fascinating. You all know the David Dunlap Observatory. This is when during the 80s, when I knew Ken, we used to basically wrap up a bunch of mirrors from up north here and make the pilgrimage down south to Richmond Hill to have our mirrors coated. And I made this rack so that the DDO can multiply coat several mirrors at once. So that was quite handy. I believe that rack is still being used today. So two parts to my talk. I'm going to explain to you how thin film coatings work. And also we're going to go over how they're applied to your optics and telescopes. So as you know, thin films can be used for a variety of things for astronomy. We use them for reducing unwanted reflections from surfaces of lenses, like eyepieces, or lenses for telescopes. We use them also to enhance the reflectivity of mirrors. You've heard of enhanced coatings. And we also use thin films for making optical filters, like O3 filters, dark sky, deep sky filters, that sort of thing. And they all use pretty much the same kind of process that I'll be explaining about, and they all work based on the same theories. But in order to, I need to digress a little bit in order to explain how these coatings work. And in order to do that, I need to kind of explain a little bit about how light works. And the best way to do that is to use wave theory by using water as an analogy instead. So as kids, we used to, throw pebbles in the pond, and we see the wave pattern basically all travel out in all directions in straight lines. And but if you ever look closely at these ripples of water, it's actually, the water is actually stayed put. It's the energy that has traveled from one spot to the other. So if you drop a pebble in a pond, in a pool, for example, you'll see the wave travel from left to right. It's actually the water is not moving. It's the wave and the energy that's moving. And and you can see sometimes if you put like a toy boat or something like that in the pool, it'll actually just kind of like it'll basically go up and down sort of thing. So just keep in point that the water is actually stayed about where it is. It's the energy that has moved. We've all heard of tsunami waves. They can travel as fast as a jetliner, believe it or not, up to 500 miles per hour. But as they get closer to the shore, they slow down and grow in height, and that's where the damage is caused. Now, marine architecture has actually used the theory of thin film coatings in order to reduce waves. And as you know, in an ocean liner, we have this huge bow wave that causes tremendous drag on a ship. And if we can somehow, and these waves, like this bow wave can be seen for hundreds of miles, and it produces tremendous drag. So we need to somehow reduce or eliminate this wave. So how can this be done? Well, this is done by introducing a second wave. And this is done by introducing a protrusion that you can see in dry docks. It's called a bulbous bow. And in dry docks, you can see this onion-looking thing sticking out in the front, but it's normally underwater. So that's why you only see it in dry dock. But what this bulbous bow does is as the ship is traveling in the water, it actually creates another second wave, but this wave is slightly different. It's not as big, however, it's only maybe about 15% as big as the initial bow wave. But as you see by the diagram, that it's out of phase. So these two waves basically add together and they subtract, resulting in a slightly less resultant wave that's only 85%. So basically, we can save almost 15% energy in fuel by doing this. I'll skip the skipping rope analogy. So congratulations, and you now have earned your degree in wave theoretical physics. Now let's observe what happens to light waves when they strike glass surfaces and other materials, such as glass. So uncoated lenses, we know that when you look at an uncoated lens, you see a lot of glare, a lot of that's because the light is being reflected from the glass on both sides of the lens. And if you have multiple lenses, it gets even worse, right? So this reduces the brightness at the final image. It also loses contrast, and the stray light is very, very unwanted. So we need to find a way of reducing these glares and increasing the light transmission through the lens. How do we do this? Well, you'll see. Let's first show exactly what happens when light enters a single piece of glass. Here we have light coming in through the air, and it strikes a glass surface. And of course, we see a reflection. And reflection is approximately about 4% on bare glass. And the rest of the light goes through. We're not going to take into account any absorption. We'll call it zero. And of course, we get the same reflection happening at the back end of the glass as it emits through. So by and large, we get basically a very low percentage of light going through the lens. That's uncoated, around 92% or so, not very good. And you can just imagine how worse it gets if you put multiple lenses in there that are not coated. So how can we reduce these reflections? Well, what we do is we add a second wave, just like the bulbous bow did, and we use thin film coatings to do this. So one of the materials that's commonly used for lenses is magnesium fluoride. It has, as you can see, it has a slightly lower refractive index than glass does, and that's important. Because whenever light strikes an index of refraction that's lower than glass, we create a smaller reflection. So as you can see here, the first reflection off the magnesium fluoride boundary is only about 2.5% compared to bare glass, which was 4%. The rest of the light goes through, unabsorbed. But then again, the magnesium fluoride, the light going through the magnesium fluoride boundary now enters into glass, which is a higher index of refraction. So we get another reflection going on here. But as you can see, the light is traveling into the magnesium fluoride a quarter wave thick, and it's exiting out of the magnesium fluoride by another quarter wave. So now it's a half a wave out of phase. And so we have two reflections that are out of phase with each other, similar to the bulbous bow. When you add them together, you get a resultant reflection that's only 1.4%. So we went from 4% from bare glass to now 1.4% reflectivity by just introducing a simple thin film coating, such as magnesium fluoride. The same thing happens on the back side of the glass. We had the same coatings there, and of course we get a much better improvement in light transmissivity. Now, this doesn't work perfectly. In order to cancel out the light perfectly, all of these conditions have to be met, and of course they never are, because we can only have a quarter wavelength of a material for a certain color of light. So we basically optimize it for in the middle of the spectrum around green or yellow, but then the reds and the blues, they're going to reflect more than the greens will. So how do we improve that? Well, that gets a little bit more complicated. I won't get into it, but that's what multiple coatings are used for. But here's the effect that you would see. When you coat a lens, let's say just in the center part, we create the optical hole effect. And normally when I give this talk live, I pass around this lens, and you can actually, no matter how you look at it through the light, you can't see no glass there. The only way to tell it's glass there is by touching it. Then you get fingerprints on it, and everybody gets upset. So, but anyway, this is the effect that happens. The coating is very, very thin. It's about 100 nanometers in physical thickness, very, very thin. But that's all else required to now get this optical hole effect. And here's another piece of, this is a picture window glass that picture frame glass that I used as a demonstration as well. As you can see, the glare off the uncoated section is quite prevalent, but the center part is coated. Now this is just with a single lens and reflective coating of magnesium fluoride. So multiple coatings involve many, many layers. Like if we wear eyeglasses or lenses for cameras, they can have 5 to even more different coatings on them, and they tend to straddle the spectrum to make the glass even thinner, almost invisible. Now let's go look at how mirrors are done with thin films. So typically an aluminum coating is very, very thin. It's about 600 atoms thick, or 60 nanometers in this case. And the problem with aluminum is that in a vacuum, it reflects 90%, but as soon as you introduce it to air, it immediately oxidizes, and you get a 10 millimeter aluminum oxide that forms on it. And this now reflects the light. We only get an 87% reflection off the aluminum. Not very good, especially if you have 2 or 3 reflections in your telescope. You would be down to 65% with 3 reflections. So not very good. So we need to improve the reflectivity of the aluminum. Now, we used to use silver in the old days. Silver was 99%, but the problem with silver is that it tarnishes. It reacts to the sulfur, and it causes sulfur sulfide to form, which is that ugly yellow appearance that you would see over the course of a year, especially if you lived in Sudbury. So enhanced aluminum coatings, you've heard the term. And all we're doing here is we're doing something similar to what we do with the lens. We're adding dielectric materials, but instead we're adding these dielectric materials onto the aluminum. You can also use, you've heard of dielectric mirrors such as star diagonals, where there's no metallic base. There's typically about 40 layers of coatings or so, and they're all done by using dielectrics materials. And these are all transparent materials, and by adding them certain ways, you can actually create a mirror that's almost 99.9 reflectivity. The problem with these types of mirrors is that they're disposable. They cannot be stripped. But enhanced mirror coatings can be stripped, and that's the beauty about them. And they can give you a lot more reflectivity as well compared to bare aluminum. And this is how we do it. So instead, we use magnesium fluoride as well and cerium dioxide, but we do the coatings oppositely that we would do in a lens. So here we're creating, let's go through what goes on. So light's coming in, and it hits the cerium dioxide boundary first, which is very, very thin, quarter wave thick, and it's got a very high index, 2.3, which is a very high index of refraction. So we're going to get a huge reflection right off the bat, 34% for the cerium oxide boundary. So the rest of the light goes through, and it hits the magnesium fluoride boundary, and we get another reflection. This reflection is about 13.5%. And then finally the light finally hits the aluminum boundary. But by that point, we've already reflected almost 47, close to 45% of the light already by the dielectric. So the aluminum coating is going to reflect basically 90. It's going to reflect whatever else is hitting it, and it's going to take a 5% loss. So basically, we have 3 reflections that are adding in phase, as you can see here, resulting in a overall reflectivity up to 95%, which is pretty good. The whole thing with the aluminum coating is that it wants 10% of energy, whatever hits it. So in this case, it's only absorbing 5% because 50% of the light or so has already been reflected by the dielectric coatings. Now this is just a very simple, you can increase this again by adding another pair of cerium dioxide and magnesium fluoride, and that way you can get up to 99% as well. But it gets pretty tricky when you do that. And it's very, very hard to do these types of coatings on large surfaces as well. So here's a chart just giving you an idea as to the efficiencies of the different types of coatings and how many reflections you're dealing with. So as you can see in a cast grain, let's say we had 3 different reflections or so, you'd be down to 66% efficiency with bare aluminum. But with enhanced aluminum, we're up to 86%, which is a 20% improvement. And then if you had silver, or a dielectric mirror, for example, you'd be up to 94%. So it gets pretty good. That's why it's a necessity that mirrors get enhanced aluminum. Some of you have high-end refractors, such as the apochromatics that use oils as well as coatings, or a combination of the two. And this is how the oilings work. So for my apochromatotic refractor, it's an oil space triplet. There's no airspace, but there's 3 different lenses. And what's nice about these oilings is that they eliminate a lot of problems. First of all, they eliminate all the internal lens reflections. They eliminate any irregularities, so the internal surfaces don't need to be figured. They just need to be more or less polished. It's not affected by temperatures, and these can be maintained clean indefinitely. Now, what the thing is, the oil is pretty expensive. It's about $150 an ounce, but you don't need very much of it to do the task. So basically, the lenses look like this. There's 3 different types of glass. As you can see, they have different types of indexes of refraction. But what we want to do is choose an oil that's in between the adjacent lenses. Okay, so so they best match. So we want this glass to disappear when we put this oil in. And that's what's nice about these oils. You can get them made to any refractive index you want, and that's why they charge the big bucks for them. But so this is how it works. So you can actually get away with just oiling these lenses and not have to do any coatings on them whatsoever. So I'll get Andrew to show you the disappearing beaker video. Simulates what happens in an oil space lens when you use the oils instead of coatings. So Andrew, you're showing the video right now? Okay. But you can see. Okay, so that's pretty much the effect, what you're seeing here. Okay, now we'll go on. All right, so that's basically how the coatings work. Now we're going to show you how they're actually put on the optical surfaces. So here's my shop here in Sudbury. Enter at your own risk. Here's a picture of the Bay Area, the lab where we do the log grinding and polishing of the optics. There's the polishing machine there, up to a 30-inch or so. I'm a collector of hot sauces as well. The coating room's in the back. We have an optical testing tunnel that's all computerized. And inside the coating room, we have got a dual bell jar system. One of them is strictly for doing dielectrics and silvering, and the other chamber is used for enhanced aluminum coating. So this is a vacuum. Most of the technology that you see here has to do with creating a vacuum. So there's a lot of pumps and also electrodes and that. And the optics, or what they call the substrates, or it could be a mirror or a lens, they're suspended upside down, as you can see here, facing down so that no dirt falls on them. And we have the vapor sources are located down below. And we got a closer look at them here. And so this is just an example of an aluminum vapor source and a silicon monoxide vapor source. We call these filaments or vapor boats. Some of the terminologies that we use here. So we use a tungsten filament for evaporating aluminum, and it basically looks like the same kind of filament that would be in an incandescent light bulb. And what we do is we hang off pure aluminum crimps, about eight of these or so, about 80 to 75 milligrams each. Everything's pre-weighed, so we get exactly the same coating thickness all the time. So a lot of current goes through this filament, about 400 amps. And what happens, the aluminum will melt at 600 degrees Celsius, and then it'll start getting hotter and hotter and hotter. And at about 1200 degrees Celsius, it'll actually boil off because it's in a vacuum. So it'll turn into a vapor, and the vapor will go in all different directions. And a very, very thin coating will actually deposit and condense on the glass substrate. No more than 600 atoms thick. Which is about 1,000 times thinner than saran wrap. So it's a very, very thin coating. You don't want to go too thick, otherwise the aluminum starts losing its luster and it'll look like a white piece of paper if the coatings are too thick. And if the coatings are too thin, then you can see light through them. So there's a happy balance there. Basically, we put a coating of 60 nanometers or so on there, and that makes it nicely opaque. Another example of some of the silicon monoxide boat. You can do silver. You can do silver in here as well. Silicon monoxide, sometimes used as a protective overcoat. I don't recommend it because silicon monoxide takes a long time for it to naturally oxidize in air, and it also reduces the reflectivity of aluminum even more so than 87%. So the enhanced coatings is the way to go. So here's the chambers when they're pumping down. So most of the work is in the taking the air out of the chamber. It's actually most of it's actually water vapor actually. Sometimes I always like to get visitors. We've had the occasional celebrities. I would drop by once in a while, like Dave Lee and Thomas Bopp here back in '97, and they signed my machine, and we spent an evening with them. So the mirrors, like I said, are suspended upside down. Here's a 16-inch mirror that we're putting in here, and you got to be careful not to drop these things. And so we start to pump down. So during the pump down, we do what we call molecular sandblasting, which is like an ion plasma discharge, where we apply 15,000 volts to the residual atmosphere. What this does, it bombards the surface of the glass with ions, so that it basically rips off all of any water molecule, because a lot of water likes to stick to things. It's like if you ever take a propane torch to a piece of glass, you'll see the moisture dissipate from it, and then you remove the torch, and you'll see the water basically reform right back on the glass. We got to get rid of this water, otherwise the coatings won't stick very well to the substrate. So this plasma discharge is used for a good 20 minutes, and it basically rips off all those water molecules off the glass substrate, making it perfectly dry. Here's a process schematic of my little chamber, that portable coating machine. Basically, it uses the same process as my bigger machine. This portable unit needs cold water to run through it at all times in order to keep the diffusion pump hot at the bottom and very, very cold at the top. That's how the system works. So it's similar to this is the picture of a diffusion pump. And the way it works is similar to your shower head in your shower. When you turn the water on, the water sprays out of the nozzles. We can imagine having 7 layers stacked on top of each other of nozzle heads. And this oil is being boiled down below, and it's going up this chimney, and it's spraying out at supersonic speeds. And so the oil is actually pushing down on the air, pushing it out, not sucking it out. And so we need to get down to like a very, very high vacuum, millionths of an atmosphere, similar to where the space shuttle flies at. Otherwise, when we vaporize the aluminum or other coatings, they'll oxidize in their travel to the substrate. So that's why we need to take out all the air as much as possible. So the pump down takes about 45 minutes to do. That's how long it takes. But the actual coating actually takes very, very little time. It only takes maybe a couple of seconds for the aluminum to vaporize. It's done in a split second. The other coatings, like magnesium fluoride and cerium dioxide, they may take up to several minutes to coat. And that's nice because you need to monitor the thickness as you're depositing those materials. So in order to get the proper enhancement that you're looking for. So here's what's inside of a diffusion pump. These are the shower heads I was telling you about. This is when I was refurbishing this machine back in the early 90s. There's no moving parts to this pump, believe it or not. The oil basically boils at the bottom in a boiler, and the oil vaporizes and it rises up into this chimney, a stack of shower heads, and then there's little holes, as you can see there, and the vapor is so strong, so powerful that it sprays downwards, and then it gets cooled by those cooling coils that are around the pump. And the vapor now basically rains down, pushing the air out where it escapes out the side. There's another pipe just above the oil where it's boiled, and that's where the air is taken outside. So this is the mirror just being coated. Now, when you ever look at a mirror that's being coated, and if it has overcoatings on it, you'll see certain features on it. And these are interference colors that you will see. And so one of the things that we do, these coatings have to be baked at a very high temperature in order to be cured properly. So they're baked in air in an oven at about 250 degrees Celsius in order for the coatings to cure. And as they cure, you'll see you can see these interference colors, and you can only see these edge on, or kind of like at an oblique angle. When you look at a mirror face on, you should not see these colors. It should be perfectly white. But on the angle, you'll see certain colors. You might see magenta, yellow, and green. And depending on the type of coating that you have, it'll give you different distinguishing colors. So the color tells us how thick the coating is. That's how we know. That's how we can tell how thick the coating is. So when we're putting on the magnesium fluoride, okay, we'll see it go from a yellow to a magenta over a few minutes, and then we stop it around a magenta color, and then we introduce the cerium dioxide, and the cerium dioxide will then change the color from magenta to green, and then the green will slightly go away. And this is face on. So, but when you look at it on an angle, you'll see these interference colors. There's the oven. This oven's never seen food, by the way. It's only seen glass. And this was this is my portable coating machine, which we brought to Stalfane a couple years ago, and it's all. I made it all Bluetooth controlled. I brought it to 2003 at Starfast, but it was a pretty simplistic machine at that time. So I've improved a lot of electronics on it and plumbing lines and everything else. So, and then with the latest Wi-Fi and Bluetooth technology, I made the coating all basically all controlled through my iPhone or on my iPad, and it was kind of fun for the spectators to basically actually operate the machine. All they had to do was push some screen buttons on my iPad to turn it on, and it would do its thing. So this is the very first mirror that we coated at Stalfane, and this member got her first indoctrination into the Springfield Telescope Makers Club by making her mirror herself, and we have, for historical reasons, we had it coated right on site at Stalfane. So that was quite a remarkable time we had there. I coated up to almost 15 mirrors that day, or that weekend, and so it was a lot of fun. That's pretty much it. I'm almost just about time out. So any questions for anybody?
Well, Alan, fantastic. Thank you so much. Fabulous information and very, very interesting. I think we're going to get a lot of questions, so I'll turn it over to Emma.
Okay, first question is, how often is the new coding applicable? What testing is done to know that a new coding is needed?
Yeah, this is a tough question. So when you look down a telescope, even a very dirty mirror will look almost not too bad. But what you do is you take a very bright light, like a big spotlight or a torchlight, what I call it, a really good light, and when you shine it down the mirror, it'll tell you that if it's, say, this doesn't look too good, it'll show its face very, very easily. The other best way to do it is to take the mirror right out of the telescope and look at it under a very bright light, like a fluorescent light. Look through the back of it. If it starts to get worn out, it'll start to thin out. So you'll start seeing the light through it. You'll see a lot of pinholes through it. What you don't want to do is make sure that there's obviously no exposed glass. That's a bad news, because if there's any exposed glass, that glass is now weathered. Okay, it's got attacked by dew. It's lost the atoms and the molecules that allow it to bond properly to the coatings. So the glass has to be always pure in all respect. In other words, like it almost has to be as pure as being taken right off the polishing lap and cleaned immediately and coated. Glass cannot be left to the environment, like rain and dew and all that kind of stuff, so it'll get damaged. So it's an unfortunate thing to go through. I received many mirrors like that they just turn into such bad shape that the only recourse is because what happens if you try to coat those mirrors, the coating will just flake right off. It's just like rust. You're trying to paint over rust on a car. You got to bring it down to a new surface again. That means sanding it. We don't do that with mirrors. We polish them and figure them, but it's the same idea. Typically, coatings should last you. Bare aluminum coatings have been known to last 3 to 5 years, but the enhanced coatings now are much durable. And the commercial mirrors now that you buy through telescopes, they're all enhanced, and they last many years. Many years. Enhanced coatings are very durable. During my talks, I have many samples that I send out to the audience, and I give them scouring pads. You know the scouring pads that you use, those green scouring pads that you use to clean your dishes with? I actually have people try to scrub off the coatings. They can't even make a mark on them. So they're quite durable physically, but still, I would treat them with great respect. Keep them out of the dew. Try to prevent them from getting wet or dew on them at all costs.
Thank you. Is there a way an amateur can measure? Is there any way amateur can measure the reflectivity efficiency of a mirror at home with basic equipment?
To get an actual quantitative result, it's kind of difficult. But here's what I do: as a qualitative result, what you do is you take a piece of like a piece of white paper, and you put it beside your mirror under a very bright white fluorescent light. And then what you do is you take 1 ply of Kleenex or Kim wipe tissue, and you place the tissue on top of your mirror and on top of the white piece of paper. The tissue on the white piece of paper will tell you what a perfect mirror would look like. Okay, so what you're going to see on your mirror is, as it degrades, it's not going to look white anymore. It's going to look very dark gray. And that's what happens when a mirror deteriorates. You can easily, so what you're doing with the tissue paper is what you're converting the specular reflectivity of the mirror to a diffuse reflectivity of the mirror. And what it does, it tells you how bad the coating is in terms of color now, because now the color is scattered. And so as the reflectivity drops, okay, the color is not going to be as white anymore. It's going to start going darker and darker. So if you've ever looked at the eye plays a lot of tricks on you. So if you ever looked at a chrome mirror, for example, or even a silver mirror, it's very odd, very eerie to look at, because actually a chrome mirror or a silver mirror, like a silver, they'll actually look kind of dull. Like it doesn't look, especially silver. You put a silver mirror against an aluminum mirror, there's something odd about it, because the silver mirror looks kind of like, doesn't quite look right. That's because your eyes are playing tricks on you. But the white piece of paper trick that does it, with the tissue. It tells you how really good the reflectivity is. So that's one way that an amateur can easily tell as to how good or bad the coating is. And another thing too, when you put the tissue paper over the coating, you'll actually see the interference colors as well. So if the coatings were put on too thick, in other words, the dielectric coatings were put on too thick, they'll stand out. They'll stand out quite a bit with doing that test. So you can actually do a lot of qualitative testing on your own without using any fancy equipment.
How long did it take you to learn this skill?
Yeah, that's the scary part. I had no. I was so naive when I acquired this machine. I totally rebuilt it, but it took me a year to get it working, and I had no idea what was involved. Like I ended up buying books on it, going online, learning from other people. It actually took me like almost a year. Like aluminum is pretty simple. Aluminum's pretty straightforward. It's kind of like whatever. But the overcoatings were quite complicated to learn how to do, and you just tear your hair out learning how to do it. But once you learn, it all makes sense. Just like everything else, I guess. But I found it's a fascinating science. It really is. It's almost like magic, that you're able to do this kind of stuff, with vacuum. Vacuum science is quite it's a very interesting science to delve in, and it's very entertaining too to watch. I wish more people would come up to visit me and actually see the progress, actually see the actual procedure. It's quite something to watch, actually. Yeah.
For oil-spaced groups, what about the glass surfaces on the exterior of the lens, where the light beam enters and exits? Are they coated normally? Yeah,
for commercial lenses, of course, they're coated as well. So that gives you just an overall better transmissivity, of course. We did a test with my lenses against a lens that was coated with magnesium fluoride, all 6 surfaces. We had it tested at a professional lab where they were able to do a full spectrum analysis for all colors. And it was very interesting to watch because my oil-spaced coatings turned out better, had more transmissivity to them, even though my R1 and the R6 surfaces were bare glass. It had more transmissivity than the air-spaced coatings that had magnesium fluoride on all 6 surfaces. So it's very inconsequential to see the difference. I would assume that for photography purposes, for sure, you would want the front and the back lens sides to be coated. But I'm more of a visual observer myself. I don't do photography, but I find it's inconsequential. And also, coated lenses, as you know, are very, very hard to keep clean. Just like I've worn glasses all my life, and it's just every 10 minutes they're dirty all the time. So it's like what's nice about bare glass is that they're very easy to keep clean, and that they can be clean right out in the field very easily. So I'm not losing much light. I'm getting still like over 93% throughput, even with my oil-spaced lenses.
Oh, are the coatings different for different scopes?
True, they are. Yeah, there's different formulas. You can design the coating for whatever you want. So, like, let's say your hydrogen alpha light or whatever. So, what you like typically for visual purposes, we choose the coatings are basically designed for the middle of the spectrum. But you can also tune the coatings for ultraviolet light if you wish. That's what they did for the Hubble Space Telescope. The Hubble Space Telescope has a simple coating only of magnesium fluoride. The only reason why they use that is because magnesium fluoride is the only coating out there that does not absorb ultraviolet light, it transmits it. So the aluminum is able to reflect it, take the light in, and reflect it back out without being absorbed by the magnesium fluoride. So that's why the Hubble Space Telescope was only coated with magnesium fluoride. Other coatings would, your ultraviolet light would be definitely degraded big time by using other coatings. So you can use different coatings for doing different for specifying certain wavelengths that you want to capitalize on, such as hydrogen alpha light, whatever. You can move the spectrum. You can optimize the coating formula so you can make it more reflective for blue light, ultraviolet light, red light, or whatever.
How long does the whole coating process take?
The coating process starts with the glass coming through the door. So it's packaged up, which takes up to several minutes to unpack it. Then the optics need to be stripped. They're placed in a solution of ferric chloride, typically, or other solutions, depending on what kind of coatings are on there, like chrome or whatever. So the coatings may take up to anywhere from a day to a week to strip, depending what type of coatings they are. Then the glass has to be chemically cleaned, and then it's placed in the chamber. And every mirror has to have a special jig made for it and adjusted. And so the actual pump down itself, once it's in the chamber, you're looking at probably a couple of hours of doing the actual. So once the optics are put in the chamber and you start the pumps up, typically it's done in about 2 hours. And then the mirror has to come out, and then it has to be put in the oven and baked overnight, and then cooled off very slowly. So, and then it has to be, basically examined and make sure everything's okay. You don't want to have to redo the whole thing over again. So, which does happen a few times, but not very often. But yeah, there's a lot of work. So basically it's almost 4 hours to do 4 hours of attention. Basically a half a day's work just to do one pump down for a single mirror.
How close do commercial telescope makers follow the meticulous approach you do? How do they differ?
They're probably doing just as well. They got better. They definitely probably have better equipment nowadays than I have right now. My machine is it's an old unit, and it doesn't use all of the fancy processes that they use now. So now they use my system is all thermal evaporated, so you're limited as to what type of materials you can evaporate with thermal methods. Some of the new coatings now use electron beam guns, so they're able to use titanium dioxide coatings, silicon dioxide coatings, that sort of thing. But those coatings are mostly meant for dielectric mirrors. So there's nothing wrong with dielectric mirrors. The only thing is, like I mentioned, if anything was to go wrong with your dielectric mirror, it's done for. You can't strip those mirrors. The only reason why is because the dielectric material is very, very close in chemistry to the actual glass. So you can't strip those dielectric materials without destroying the glass. So if anything goes wrong with those dielectric mirrors, you got to throw them away and buy new ones. So what's nice about the thermal process is that I'm using a mirror coating first, which can be stripped, and then on top of that, I put the dielectric mirrors coating, so they can be. So the whole mirror can easily be stripped if you have an enhanced mirror coating that has a base layer of aluminum on it. So the coatings are quite durable, even still, but I'm limited as to what I can do for anti-reflective coatings. So I can basically only do the magnesium fluoride coatings at this point. I can't do that. I'm not capable of doing the multi-layer coatings that you see commercially.
We have one last question. Paul wants to know if his Schmidt-Cassegrain telescope is 16 years old. Should he be worried about the coatings on the mirror and the corrector plate?
No, I've seen those mirrors last, because they're sealed. They typically last quite a long time. It's the corrector plate. That's the problem with the corrector plates. They can't be stripped. Okay, those are dielectric coatings on there. So, yeah, the problem with that is that those coatings on the corrector plate, if they were to go, unfortunately, you cannot strip those coatings. So they got to be brought back to the manufacturer and either replaced or whatever. So, but the mirror should be fine unless you see like any black spots or anything like that. Yeah, that's unfortunate with the Schmidt cast screens. If the correct, but you know, with the multi coatings, so like I said, the multi coatings of today, they should last a pretty long time. The older coatings, back in the 70s and that, I don't know when they started introducing multiple coatings on Schmidt cast screens, but the earlier coatings were just magnesium fluoride, and they would only last so long. Actually, they would only put the magnesium fluoride coating on the inside surface of the corrector only, because the outside coating would be more easily damaged by environmental attacks. So it was, for a while they actually just coated the inside surface of the corrector. But with the multi-layer coatings out there today, they're super durable. If you keep them, if you take care of them, they should last you a lifetime.
All right, thank you so much, Alan. Lots of useful information, and I'll bet you we can probably go for another 15 minutes with questions, but we have to move on. So thanks to our speakers, Andy, Jenna, Alan, and for Steve for making a special appearance. Right, so let's move on to our president, Tom Luton, with the announcements for this evening.
And thank you very much. And good evening, everybody. Once again, we've had a wonderful evening. Lots of interesting talks, but let's get on with the announcements. So, as Paul mentioned earlier, we've got two types of meetings. We here have just had a recreational astronomy night meeting, and we also have speakers nights meetings. Both of these are, well, you can watch them live here on YouTube, and they're also going to be available in recorded format for you to watch later on at your convenience. So if you're here for the first time, please say hello. Enter some questions for the presenters. If you're a new member, introduce yourself. And if you're coming from far, far away, please let us know where you're from. So our next speakers night, and it's the last speakers night before we break for the summer. We don't have speakers nights during the summertime because it's rather hard to get speakers. Folks are away on vacation or on sabbatical. So our next talk is on the 19th at 7:30 p.m. right here on YouTube. Dr. Claire David, the assistant professor of physics and astronomy at York University and an associate scientist at Fermilab, will be talking about what is Dune. Embark on the underground telescope to pierce the secrets of matter. Right here on YouTube. Our next recreational astronomy night is the 2nd of June, 7:30 p.m. Chris Vaughn will be handling the sky this month, and as Paul said earlier, we've got 2 vacant spots. If you'd like to present something, please drop Paul a note. So, because of the COVID outbreak, our world-famous education and public outreach activities have moved online. We have done and are planning virtual star parties and EPO talks with the Ontario Science Centre at Millennium Square, David Dunlap Observatory, the St. Clair O'Connor community, the Dunlap Institute, with Brownies, Cubs, Scouts, and school groups, and as well our New Observers to Visual Astronomy course. More details can be found by contacting public education at rascto.ca. Unfortunately, because of the outbreak, all of our observing sessions at Bayview Village Park, Long Sault Conservation Area, and the Ontario Science Centre are suspended until further notice. The Carr Astronomical Observatory is closed until further notice. Maintenance activities only are going on. We are not having a spring work party this year because of the outbreak. But in spite of all that, we still have a need for volunteer help. So if you're a RASC Toronto Centre member, if you're interested in helping, if you've got some free time, please contact our volunteer coordination team at volunteer@rascto.ca. Just a few samples of some specific roles we're trying to fill. We are looking for a new observing committee chair and some committee members. We're looking for a light pollution committee chair. We're looking for a national council representative. We're looking to put together a marketing committee, and so we're going to need a chair and committee members. Our AV committee, who has been putting together these wonderful programs, is in need of some help. As well, we need some additional help for education and public outreach on the committee and to operate telescope camera operators for our virtual star parties. Contact volunteer@rascto.ca. Our stellarium training courses are continuing. The May 31st course, level 1, is full, as is the level 2. June 21st is full. And the level 3 course, which we don't even have a date yet, is full. We have a Mobile Plus course in the works coming soon. We're bringing on board new trainers to expand our operations. We've got a waiting list, rascto.ca/content/stellarium training series. The 2021 RASC General Assembly will be online this year, June 25th to the 28th. Keynote speaker is Emily Calandrelli. I probably mispronounced that. I apologize. The cost for the event is $15 for members and $20 for non-members. The RASC annual general meeting is during the General Assembly, and that specific program is free for all members. More details are available at www.rasc2021ga.ca. And this is the part where I get to plug membership in the RASC. There are currently some technical issues going on as we're updating the database, but if you can't get through right now, you'll be able to get through fairly shortly. Please renew online at secure.rasc.ca. If COVID has resulted in some financial difficulties for you, be advised that we do have a RASC emergency fund. It's completely confidential. If you're interested in that or in giving a gift membership, please contact Adela at the national office at mempub@rasc.ca. And with that, I'd like to wish you all a very good evening. Thank you very much for joining us. Thanks again to our AV team and our speakers. Please follow us on all social media. Be safe, keep looking up, and have a good night. Take care.